Let's talk about the upgrades of the Large Hadron Collider. First, let's start with the basics. What is the Large Hadron Collider? Well, the Large Hadron Collider is the biggest experiment ever built. It's 27 kilometers long and is located in the border between France and Switzerland. And how does it work? Let's take a bunch of protons and let's inject them into the LHC. Beam 1 circulates these bunches clockwise. On the other side, we inject another bunch of protons and circulate them anti-clockwise. Now we circulate both beams until we reach an energy of 7 tera-electron volts. Let's make a parenthesis here to understand how much 1 tera-electron volt means. 1 tera-electron volt is equivalent to the energy of a flying mosquito, but in this case, this energy is stored in a space a million times smaller. Getting back to the LHC, once we reach 7 tera-electron volts of energy, we smash the two beams together in the location of the 4 experiments: Atlas, Alice, CMS, and LHCb. But now, why is this accelerator so big? Let's go back to a basic question. What are we made of? In fact, what is all matter made of? Well, we know that atoms are the basic building blocks of everyday matter, but it wasn't until the beginning of the 20th century that the real study of the structure of matter began. It was discovered that atoms were made of even smaller particles called protons, neutrons, and electrons. But what are protons, neutrons, and electrons made of? And how about all these other particles that were being discovered? They normally have very short lifetimes, but they were detected from cosmic rays, which are really energetic particles coming from space. Well, they're made of quarks, at least some of them, like the protons, neutrons, or kaons, and they were named the hadrons. On the other side, the other particles like the electrons or the neutrinos were theorized to be fundamental by themselves and were named the leptons. So, the theory of the Standard Model tells us that 6 quarks and 6 leptons made up for the entire matter that we know, and they interact with fundamental forces via other particles called bosons. All this work in theory, but how was it proved? How do we study something that is so small? And also, how do we study particles that disappear so quickly? To give a sense of how small everything is, let's compare the size of an atom to a human. This is equivalent to the size of the human and even 1 order less to the diameter of the Sun. Well, it was discovered early on that colliding particles was a recipe to study them. Let's take the example of the LHC. Inside the detector, the two beams encounter and produce collisions. Then all this energy is converted into matter, as we know from this very famous formula. So, many different particles are created from just colliding protons. And if we accelerate the protons fast enough, we can get the massive evasive particle that we want, and the evidence of its existence is studied in the detectors. So, different accelerators were built to collide different types of particles. Physics profit from having these different kinds of collisions, since they all provided important discoveries to prove the Standard Model theory. Until before the LHC, all the particles had been discovered, except one. The Higgs was the last piece of the puzzle, but it was theorized that if it existed, it needed a lot of energy and a lot of statistics. So basically, a Large Hadron Collider was needed. And finally, in July 4, 2012, after 3 years of data, a Higgs-like boson was discovered in experiments CMS and Atlas, reaching a milestone in the understanding of nature. So what's next for the LHC? Well, there are still some unanswered questions. Among some important ones are: how do we explain the physics beyond the Standard Model? And also, why from the very beginning is there more matter than antimatter, which is the very basic core of why we exist? Well, the upgrade plans of the LHC contemplate an increase of energy up to 14 tera-electron volts, make the particles go faster. Also, plans to increase the luminosity, which are the amount of collisions per meter squared per second, are already on the go, and plan is to start getting data in 2020. I work in another upgrade plan for the LHC. The LHC aims to take electron-proton collisions also into the tera-electron volt era. So, the plan is to build a new accelerators for the electrons and collide it with one of the proton beams of the LHC. I work in the design of the interaction region of this collision. The task for this design is to collide the electrons with proton beam 2, while the other proton beam 1 bypasses the interaction. So I take all the elements of the accelerator to find the best design that will give me more collisions with less damage on the detector. So, in the end, why do we keep building bigger and better accelerators to study something that we don't even see? Well, because all this so-called fundamental physics from 100 years ago has helped develop all the technology that we use nowadays. And also, as physicists, we aim to keep building the tools to unlock the mysteries not only of the Earth that we live in, but of the entire universe.